And here comes one of the most beautiful problems of circular motion, that is Kepler's analogue for circular motion. As you can see on the screen, there are two small blocks placed on the inner surface of a smooth vertical conical funnel. Well, and they are sliding with constant speeds, not along the cube, but they are sliding with constant speeds at height h1 and h2. Well, from the tip of the cone. Their heights are fixed. Write down an analogue for Kepler's third law, that is, find the ratio of the squares of the period of revolution of the blocks around the axis of the cone. And this is interesting. And to solve this, you can consider the motion of one of the blocks moving with a constant speed v along a circle of radius r at a height h. Let me show you a picture. I have considered this one. Just I have a block moving with a constant speed v along a circle of radius r at a height h from the tip of the cone, just one. And you can see here the block is acted upon by the force of gravity and the normal force, that is normal to the surface of the cone. And I would like to write the equations of this small block as the projections on the vertical and radial direction, because they are basically moving in a horizontal plane, and all the vertical forces acting on it are simply balancing each other. They are not participating in any circular motion, because circular motion is in horizontal plane. And in your life you have solved many of the problems like this, so that this angle you can see here is alpha. That means vertical and surface of the cone, slant height and height of the cone, they make an angle alpha with each other. वर्टिकल के साथ इसकी कोन के सरफेस के एंगल अल्फा है. You know, the horizontal is perpendicular to vertical. Oh, that's a great knowledge. And normal will be acting perpendicular to this surface. So इन दोनों के बीच में horizontal और इसके बीच में भी एंगल अल्फा ही होना चाहिए, I guess. So n will have two components, n cos alpha along the horizontal, n cos alpha along the horizontal, and n sin alpha along the vertical. N sin alpha has been left with one single job, that you have to balance the force of gravity. So I am going to write down n sin alpha is equal to mg, and this is our equation 1. And in what, let's see what the n cos alpha is doing. It is providing the necessary centripetal acceleration. So I am going to write down this n cos alpha is equal to mv square by r. And look, there is a relation between r and h. R is this and h is this height, and this angle is alpha. So you would like to write tan alpha equals r by h, so that r becomes h tan alpha, and we have those three equations. And solving all these three equations, putting the values one from another and manipulating all those things, you will be getting v equals under root gh. So the period of revolution of this small block will be simply 2 pi r upon v, and put all the values, you will get this is 2 pi tan alpha under root h upon g and nothing else. And everything in this is constant except h, g, alpha, pi, everything is constant. So you would like to write as t is directly proportional to under root h, and you got it. T square is directly proportional to h, and you will be writing now t1 square upon t2 square equals h1 upon h2, and that is the analogue of Kepler's third law. Yeah, got it. Thank you very much. And all we know, all of us know, finding maximum and minimum tension in the string while moving in forming a conical pendulum and all those things. So I'm not going to waste my time in solving those kind of problems. They are very common these days and you can solve it as well. So thank you very much for watching. And now I will be moving towards the conservation laws. Conservation laws for me are a single entity. That means mechanical energy conservation and momentum conservation. And boy, this is the home of some of the best problems in this world. So I'm going to solve them after uploading all these things. Thank you very much for watching.